opportunity in the first video to kind of review some of the labs that we did last semester and review the lab that we did today in class on our first day. So we actually started our discussion of forces with a lab that was pretty straightforward and actually not that interesting. I gave you a spring scale, and what you did was you put some masses on this spring scale, and what you would do here is you would look at this mass and you'd notice that you had a mass in grams, and you would convert that to kilograms. And of course the way you would do that is you would take your grams and divide it by 1,000, and then you would get kilograms. And I think what we did was we ended up going from 0.2 kilograms all the way up to 1.0 kilograms. And you were just putting these various masses at the bottom of the spring, and then you were reading up here, you were reading the spring scale, and that would give you the weight of the object. And of course, if we're going to draw a free body diagram of this situation of a mass hanging on a spring, what you would draw is you'd say, well, there is the force from the spring in this scale, and there's the weight of the mass due to the earth. And since it's just sitting there, what we conclude is that the force of the spring has to balance the weight of the mass. So when I read this spring scale weight, or this spring scale force, what I'm really reading is the weight of the object, which means the force that the earth exerts on the object, because let's remember that weight is the force on m due to earth. And of course what we actually had you do in lab last semester is that you actually do a plot of the weight of the mass due to the earth versus simply the mass itself. And you got a graph that looked like this. You'd go from 0.2 all the way to 1 kilogram. And you actually ended up going up to 10 newtons on the scale here. And so it was actually a pretty nice and straightforward correlation. You get 2 newtons of weight force for every 0.2 kilograms of mass. And when you did this, what people concluded is they said, you know, I can get the weight by taking the mass in kilograms and timesing it by 10. And what a lot of people were able to do is they said, wait a minute, weight is something that connects to gravity. And they asked themselves a deeper question, and this is really the conclusion that we were going for. And I didn't tell you this in class. Almost everybody deduced this. What they said is, hey, wait a second. What causes weight is the gravitational pull of Earth. So when we say weight is the force on m due to Earth, what we really mean is due to Earth's gravity. And if that's the case, maybe this 10 that we were measuring here is in fact exactly the 9.8 meters per second squared from kinematics. And so we actually came up with our first equation of the semester that we're going to be using today. So the whole point of the weight versus mass lab was to come up with the relationship weight equals the mass of the object times the gravitational pull of the planet that it's on. So that's kind of the first big formula that we're going to be using. Okay. So that's really like our first, that's our first formula of the school year, of the semester. We actually used this last semester, but I told you we weren't responsible for it on the exams, so now we're going to be using it this time. So the whole point of the weight versus mass spring scale lab was to actually come up on our own with a relationship that weight is the mass times the gravitational pull of Earth. Then we did a little bit of work with the marble and the dry ice, and if you remember, we had a marble spinning around in a circle. And what we noticed is if we have a marble spinning around in a circle like this, you know, and we had the cup over the marble, so we had a setup like this. We had a table, and we had a cup, and we had a marble inside the cup, and we'd kind of spin the cup around and around. And the instant we let the cup go, the marble would shoot off at this tangent velocity. And what we concluded was, in the absence of a force, something moving in a circle will stop going in a circle and instead moves in a straight line at constant speed. So that was one little conclusion that we got. So this is one little piece of the puzzle. That was from the marble. Then what we did is we played, so that was the first part of our little lab. And then the second part of our lab, we actually played air hockey with an eraser, paper, and the fun one was dry ice. I'll put a little smiley face by dry ice because it was fun. And of course the reason it was fun is dry ice doesn't slow down. And what we realized is that, in fact, it's not, when we push something across a table, this is sort of what we thought. We thought if we push something, it naturally stops. That's what we thought. And this is wrong. That was what we came up with from the lab. What we concluded from our lab was, in fact, if we push something, when we are done pushing, it stays in a straight line at constant speed. And then we realized a second part to this. If it slows down, something else is pushing it. If it slows down, something else is pushing it. And that's the idea. So what we did is we took the idea from part 1 and part 2 and we formulated a completely new idea. And that new idea was Newton's first law, which will actually state, hopefully I can expand this thing. Let's see. So that's not going to work. So let me just see if so yes. So here's what we got. We got Newton's first law, and this is what we deduced from parts 1 and 2 here. This one here, and this one here. We were actually able to deduce Newton's first law, and this is what Newton's first law says. What it says is that if something is at rest, it will stay at rest. If something is moving, it will stay moving in a straight line and at a constant speed. If an object slows down, speeds up, or changes direction, that can only happen if an outside force makes it happen. And here are some results, here are some consequences of Newton's first law. First, if something is not moving in a straight line, a force has to make that happen. 2, if something slows down, that doesn't happen naturally. Rather, some force must make that happen. And finally, if something is to get something moving, I need a force. And to slow it down, I need a force. Once I get it moving, in the absence of friction, I am no longer applying a force, and it continues in a straight line at a constant speed. The instant I stop touching it, I am no longer applying a force to it. So these are all things that I've written down here, and you actually have to learn, know these things. So you want to make sure that if you're puzzled still, you watch the videos again, and if it's still kind of confusing you, you want to come see me after school with specific questions about specific concepts in the videos that don't make sense. Now, I want to move on to the last experiment that you did, the most recent one, which you did like today or yesterday, depending on when you're looking at this video. And the experiment looked like this. It was what we call a modified Atwood's machine. So I had this mass m here, and I have a little mass m here. And to use loose language, what we're saying is little m, and this is really not strictly speaking correct, but it's a good model for our first pass through. Little m is pulling big M with a force. And for the purpose of this lab, I know that we normally call it tension. We're going to call it F here. And that F is transmitted through this rope. And what we wanted to do was figure out the relation between or among F, big M, and the acceleration of big M. And here's what we found. The first thing we noticed is that we actually made big M vary. And here's what we found. What we noticed was that the acceleration of big M gets smaller as M gets bigger. And in fact, we found that this acceleration was proportional to 1 over m. So that's the first thing we tested. Okay. The second thing that we did is that we actually took a look at little m here, and we said we made little m bigger but kept big M constant. And what we noticed with that is if we make little m bigger, then that makes this force F bigger. And so what we found was that the acceleration is actually directly proportional to the force. So what we were able to conclude is that the acceleration of big M is in fact directly proportional to the force we apply to it and inversely proportional to the mass. We're using a little bit of math here. And so what we came up with was this relationship that the force, the total force applied to an object is equal to its mass times its acceleration. And this is the big idea that we studied. And what we're going to do in the next video is we're going to explore this idea a little bit more, and we're going to actually talk about the idea of the net force on an object that I'll write like this, and you'll also see it written as F net. And what I mean here is I mean the total force acting on an object gives rise to an acceleration that also depends on the and that acceleration also depends on the mass of the object, because the bigger the mass, the smaller the acceleration. And we actually call this mass, as far as we're concerned, it's another name for what we call inertia, which we'll get into in a little bit in class some more. So what we're going to focus on in the next video is actually taking this equation and applying it to some abstract problems. And I'm going to show you how to get good at problem solving in the next video.